Hello, welcome back to this course on combustion in air breathing aero engines. So, as you have seen in last few classes, quite a few classes that we have done, we have covered chemical equilibrium, we have covered the theory of chemical kinetics, the collision theory, then we have covered the transition state theory, law of mass action, and then in the last two classes you have seen that how we have essentially gone over the concepts, how the theories of the chemical kinetics can be used to understand combustion kinetics, how actual fuels like hydrogen, carbon monoxide, methane actually they undergo oxidations, and then under what state they can basically undergo rapid oxidation to release a large amount of energy in a very short amount of time. Okay, so we have gone over that. So we have covered quite some amount of ground on chemical kinetics, both from a theoretical viewpoint as well as from a practical fuel viewpoint, and then we have also seen how pollutants are formed, NOx, soot, etc., and how we can actually reduce the mechanisms. But it is actually not only just chemistry, not only just kinetics or chemistry that is happening inside combustor, and combustion is much more than chemical kinetics. Now why? One of the things that the flow inside a combustor, if you just consider a snapshot of the flow state of the flow inside any combustor, say a gas turbine engine or a scramjet engine, rocket engine, any even a car engine, it is hardly homogeneous. Okay. So far we have discussed basically chemistry or combustion from a in a state where everything is homogeneous, and basically it is a perfect mixture of different kinds of species. There can be more species, but there is no spatial variation or the spatial non-uniformity of the species in the state. So that is what we have studied so far. But what I want to say is that this is not the reality inside a combustor. The flow inside a combustor is hardly homogeneous. It is strongly non-homogeneous in terms of temperature, that is in terms of enthalpy, in terms of sensible enthalpy, in terms of momentum, okay, and also in terms of species concentration. Why? Because you see, in a combustor, what is there? Combustor, the flow is essentially more or less the flow is shear flow. Okay, so there is strong shear. So the momentum of one region of the combustor, the momentum of a flow of one region of the combustor is different from the momentum of the flow in the another part of the combustor. Okay. Furthermore, the energy. The combustor contains a flame. Okay, so the region inside the flame, the flame where the flame is located, the temperature is high, and also the temperature is high in the product gases. But outside in the cold reactants, there is no high temperature; those are cold. Okay, cold means that not compared to the cold compared to the product gases. So there is strong temperature gradients, there is strong gradients of velocity. Okay, and also there is strong variation in species concentration. Why? Because in the flame region you have consumption of the fuel and the oxidizer, so those goes to 0, but outside you have got very strong concentrations of fuel and oxidizer outside the flame. But so similarly inside the flame and inside the product you have strong concentration of CO2 and water, but outside you do not have these species. So flow inside a combustor is non-homogeneous in all possible ways. Okay, it is non-homogeneous in temperature, non-homogeneous in species concentrations, non-homogeneous in momentum. So what happens when there is a non-homogeneity? If you consider the non-homogeneity inside a system, the system does not allow non-homogeneity. Okay, so the system acts in such a manner that this non-homogeneity or this non-uniformity of this temperature or this species concentration or this momentum is homogenized or it is made uniform in some possible ways. Now why this must happen? This is because from a microscopic point of view, you know that this that even though we have these field equations, but in microscopically they all these gases contains a large number of molecules, and these molecules are always in a state of motion. So these molecules always collide. Okay, so as they collide, this information of this or this high temperature or this high energy, high temperature, high concentration region, that this is basically this non-homogeneity in this type of parameters is basically is made uniform through this continuous collision of these molecules. If there was no collision, then this could have this non-uniformity could have persisted, but because there is strong always these molecules are in motion, and because there is continuous collision among them, this non-uniformity of this properties of in terms of enthalpy, in terms of species concentration, in terms of momentum is not tolerated. Okay, but how does it happen? So that is what we are going to understand today by this topic called transport phenomena. So we will understand the theory of transport, and then we will look into the coefficients which control this transport, which are parameters of which are functions of the composition of the gas, or the nature of the molecules of the gas present in the gas, and then we will find some non-dimensional numbers, useful non-dimensional numbers that will be used in this that will utilize this diffusion coefficients or this transport coefficients and these non-dimensional parameters you will see that will be useful in terms of understanding the different kinds of governing equations and the flow systems that we encounter inside a practical combustor. So as we said that if you go to the introduction, we will say that this transport phenomena, okay, the transport phenomena, what does this deal with? This deals with the transfer of properties such as momentum, mass or energy from one region to the other. Okay. So this as I said that this occurs when there is this transfer occurs when there is strong non-uniformity in these things, in this momentum, mass or energy. Okay. Now there can be two kinds of essentially transport. Diffusion transport, which is the topic of this class. This diffusion is transport due to spatial gradients in its property. So mathematically, how do we say that this some property or some parameter is non-uniform over a field? It is quantified by these spatial gradients, right. So if the gradients are 0, we can say that this quantity is uniform or this homogeneous, whereas if there is a non-homogeneous, this will be characterized by the spatial gradients of that property. And these process basically attempts to restore spatial uniformity of that property. Okay. Now in contrast to diffusion, convection is essentially bulk movement of the fluid medium. Okay. So its diffusion is not bulk movement. Diffusion is essentially one species moves from a region of high concentration to a region of low concentration, but when there is a low concentration of species A, that means there can be a high concentration of species B. So essentially species A is moving in this direction and species B is moving in this direction, where we say that this is in this region there is a high concentration of species A and this is high concentration of species B. So there is no bulk transport as such, that is what we want to say. Okay. It is only that this particular species move in different directions, whereas convection is characterized by bulk movement of the fluid medium and relevant properties carried along with it. Okay. So that is the bulk, that is the difference between the diffusion and convection. One is movement of certain kind of species, whereas convection is the bulk movement of the entire fluid medium. Now convection, this can facilitate or retard diffusion depending on the sign of the depending on the direction in which diffusion is happening. With respect to the direction of the flow, convection can facilitate or retard diffusion, and convective transport depends upon fluid motion. Okay, whereas diffusion really does not depend upon fluid motion. So that is how essentially you will see that it is the entire fluid and kinetics will be connected. Convection is basically contains the information of the fluid motion, and then we will see diffusion essentially connects with that property over small length scales, and then this thing will connect with the reaction. So we will see that when we go into the governing equations in the next few classes. Whereas diffusion transport may vary for mass, momentum or energy. Alright. So phenomenology, we basically by diffusion we do not only mean diffusion of species, we mean a diffusion transport of essentially heat which is happens when there is a temperature gradient, diffusion transport of momentum when happens there is a velocity gradient, and diffusion transport of species when there is a concentration gradient. Now, just to give you an example, I am sure you are all aware of this. Now, let us consider these two parallel plates which are at two different temperature, Ta and Tb, and Ta is greater than Tb. And of course, if this the gap between these two plates, these two different temperature plates is filled up with a fluid medium, or a solid medium as such is also possible. Suppose we consider a fluid medium, then we know that there will be transfer of heat from this high temperature region to the low temperature region, and this we call diffusion of heat. Okay. Now, similarly, if there is a concentration difference. So, this is at high concentration, suppose these are like porous plates, and this inside these there is a this high concentration of Ca, and this is the concentration of a certain species is Ca, and then the concentration of the same species on this plate B is essentially Cb. So, and then they are separated by a fluid medium. So, then because Ca is greater than Cb, which are the concentrations of the same fluid, okay, and so then there will be a net transfer of this species from this plate to this plate, okay, and that is the direction of diffusion. And momentum, suppose that this plate is now moving. Okay, this plate is now moving with a velocity Va, whereas this plate is moving with a velocity Vb, and if the velocity Va and Vb are related by Va greater than Vb, so then we know that momentum will be transferred from this from the fluid from this A to B. Okay. So, these are the different modes of transport: heat, momentum, and species. Now, this diffusion is essential for subsonic combustion. Okay. Why? Because we will see that one of the reasons is that why diffusion is essential is that because we know that combustion, you see, have seen that combustion is characterized by large activation energies. Okay. And we have seen that previously when you have large activation energies, these reactions become concentrated in very thin regions. Okay. So, as a result of this, because the reactions are concentrated in a thin region, the change of species and the change of temperature also occur in a reasonably thin region, not thin medium, but thin region as such. So, what I want to say is that this because the large activation energy because of the large activation energy, the reactions that characterize combustion are concentrated in very thin regions in space or in time. Okay. And because they are thin region, because if they are concentrated in thin region in space, then it automatically means that the gradients of these properties of either the temperature or the species are very high, and when there is a sharp gradient or there is a sharp change in concentration or there is a sharp change in temperature, then it means that as we see that, then it means that this diffusion becomes very important, and this second order transport of this high order second order derivatives, which characterizes the diffusion transport, we will see that the diffusion transports appear as second order derivatives in the species equation or in the energy equation, and they become the controlling process instead of convection inside a flame. Okay. Outside the flame, convection can be important, but inside the flame typically we will see that diffusion processes of heat and species become very, very important. All right. So, that is why we need to understand diffusion, and here we will see that the phenomenology of diffusion, and we will what we will do is that we will derive how we can characterize the flux of a property, how the property is transported across a plane, and how we can arrive at a very fundamental from using just basic principles, how we can arrive at that how will the rate of how the rate of change of that or the flux of the property across a plane, how that quantity can be derived from very basic first order principles. Okay. And that we will use to basically find out the diffusivity. So, as we said that before, that as we see here, that convection is a first order transport, right, and all properties are transported at the same rate, that is with the flow velocity. So, there is no problem. So, if you have even if you have different species at different concentrations, convection will transport them with the same fluid velocity, which is u. But we will also see that in certain cases, especially when it comes to like things like multi-phase flow or this two-phase flow, when we will study this droplet combustion, then the bulk flow velocity can be induced by the diffusion. So, diffusion can generate convection in certain cases, and as an example will see that the depletion of water from a cup through diffusion, water vapor from the surface. So, as we know that there is a continuous evaporation of water vapor from the surface. Now, for continuous evaporation to take place, there must be continuous bulk supply of water from the entire fluid, and that basically is the Stefan flow, and that will do. So, this depletion of water from a cup through diffusion of water vapor from the surface to the ambience will be high vapor concentration to low vapor concentration. We will see that that will induce a flow, and that will be essentially the Stefan flow. Okay. So, there can be diffusion generated convection, all right, and then we will study that the diffusion will look into diffusion coefficients from an elementary point of view, and for an elementary derivation we will use this collision theory of reaction rates, and following assumptions will be made for the simplification. So, what we will do now is that we will derive the formula for diffusivity, that is the parameter that controls the rate of diffusion. Okay. So, for an elementary derivation, we should as we said that this will be inspired from the collision theory of reaction rates, and the following assumptions would be made for simplification. So, we will assume that the gas in which the diffusion is taking place, that is sufficiently dilute, and only binary collisions were important. Now, if you remember that we have also used the collision theory in deriving the reaction rate constant K. Okay. So, this is also, so we can ask that what is that is also derived using collision rate theory or collision theory. Diffusivity also is derived using collision theory. I mean, yes, both are actually happen due to collision between molecules, but then when you have reaction, you basically have change in the electronic structure of the molecule. In diffusion, there is no such change. Okay. And we will accommodate in the theory doing this by saying that only when the collision energy is of beyond a certain kind of energy, that is activation energy, collisions trigger reactions. But in this case, we will just find out that what is the flux of species concentration that is happening because of these collisions. So, and of course, so no such concept of activation energy come in, all right. So, that is the difference, and we will assume that the gas is sufficiently dilute, and only binary collisions are important, all right, and so that only there is no three body collisions as such, because if the gas is dilute, that all three molecules cannot be at the same place at the same time, and we will see that this transport will only occur in the z direction, which will be the vertical direction, and the exchange of property occurs within one collision, and that is the mean free path. This diffusion is essentially an exchange of property, that is the high concentration goes to the molecules of high concentration basically travel this if you have two regions separated by high concentration and low concentration, then after certain time there will be uniform concentration. That is the property as basic essence of diffusion, and so we need this to equilibrate this property, we need basically collision of molecules, and we will assume that this exchange of property, this occurs within one collision, that is within one mean free path, and we will assume that collisions are elastic and no change in the internal structure of the molecule, all right. So, basic so then using this we go back to our previous discussion of the same basically same schematic. These are the two molecules which are essentially colliding. One has a diameter of sigma I, one other has a diameter of sigma j, and their reduced mass is given by this sigma. Their reduced mass will be given by mij is given by this mi times mj divided by mi plus mj, whereas this collision diameter is given by the sigma I plus sigma j. And also if you remember that we use this thing, that is Vij for mean Vij is the average molecular velocity obtained from Maxwell velocity distribution function, and sigma ij is, as you remember, is the diameter of the collision volume. That this is a maximum diameter within which these two molecules must be located for collision to happen, and as you remember that K0 is the Boltzmann constant. Okay. So now let us consider this schematic, okay, where we have essentially 3 parallel planes, alright. So our this is the z coordinate, this is the x coordinate, and this is the y coordinate. Say this is our origin, okay, and through the origin this plane O passes, okay, and now from L distance from the origin we have another plane A, and from L distance below the origin we have below O plane we have another plane B, alright. So now we can write by using Taylor series expansion that this property at this xi L is equal to xi 0 plus L times d xi dz at plane 0, right. So this is what we have written, and this can be easily obtained by Taylor series expansion, and also we can write up to first order test letter Taylor series expansion, and we can also write xi minus L is equal to xi 0 minus L times d xi dz at 0. So at both that we can write this at both at plane L, and this is xi at plane of minus L, and whereas this xi, this can be any property as such. Here we do not specify the property and we just consider a generalized property, okay. And then the flux of this xi carried by this mean velocity, that is the average molecular velocity, is given by nothing but this f xi, which is the flux of xi carried by mean Vij, is given by minus mean Vij. The minus sign comes as you know because this flux is travelling from a region of high xi to a region of small xi, large xi to small xi. So that is where the minus sign comes in. So it is given by this f xi is equal to minus Vij times xi plus L minus xi minus L. Okay, so this is basically the basically the flux of xi is nothing but the difference between these of this property between these two planes, and that is carried over by a mean molecular velocity mean Vij. So then it is given by, we can substitute this thing, we can substitute this from this and this from this, and we can write here this one which is minus 2 Vij times L. Okay, L is the distance between these two planes times dz at this plane 0. Now what is L? Now if you remember that we assume that the exchange happens within one collision itself. Now then what is the distance between one collision happens? That distance of one collision is of course a mean free path, that is average length, of course average distance, and that is given by this number density times pi times sigma ij square. So sigma ij once again is the diameter of the collision volume. Alright. So and then of course we know that mean Vij, that is given by this 8k0t times divided by pi mij to the power of half, which comes from the Maxwell Boltzmann velocity distribution. We used this formula in the previous kinetics class also when we derived the formula for the k. So we can substitute L, we can substitute Vij into this equation, and then we get this form. That is the f is f xi is nothing but minus 2 times 8k0t divided by pi mij to the power of half times 1 by n pi sigma ij square ij with subscript ij times d xi dz. Okay, and this derivative d xi dz, as you see, comes from essentially this from the Taylor series expansion from here and here, from here and here. Okay. So now we can consider, now instead of this generalized formula that we have derived, we can use this for different kind of transport. We can use this for species transport, we can use this for momentum transport, we can use this for energy transport or thermal transport. So here as you see that this xi, now we write this xi is equal to ni times mij. Okay. Ni is nothing but the number density of this ith species, and Mij is the reduced mass, Mi times Mj divided by Mi plus Mj, and this is the species transport, and then this is xi, and we can then supplement, we can then substitute d xi dz, and then the associated derivative of this, that is dni dz, and we can write dni dz into d rho I dz. We can convert those things with appropriate constants, and then we can try to find out the mass diffusion coefficients, and if we do that, we will find that this f species I, the flux of the species I, is essentially given by minus d ij times d rho I dz, whereas d is given by this formula. So, essentially this is the binary diffusion coefficient, which is nothing but 2 times 8 a mij times k 0 t divided by pi to the power of half, okay, and divided by rho times pi I sigma ij square. So, the two most important thing is that you see this gives you a t to the power of half power dependence and 1 by rho power dependence. This Mij power dependence is actually, we can this is not fully refined, this we have made many assumptions, and we will see that this can be have a more defined formula if we introduce some more complexities. But for this is also itself good, it shows very importantly that Dij is temperature to the power of half. Okay. So, as you increase the temperature, diffusivity increases. The reason is simple, the reason is that essentially as you increase the diffusion, your mean molecular speed Vij, which is 8 k 0 t divided by pi Mij, this one essentially is increasing. So, there is clearly there is very fast transport happening when there is more Dij. So, that is where this t to the power of half come in, alright. Now, also now momentum transport, if you say momentum transport, now we write this property xi, which was a generalized property, as n times Mij, which is for the mass, and then times then the Vy, and then we will when you take d xi dz, essentially becomes dvy dz, and then we have find out the viscosity coefficient. So, if we write this, the flux of momentum transport is given by minus mu ij times dvy dz, which actually comes from the previous formula of f xi is equal to something times d xi dz. Okay. So, this something as you put in different forms of xi, whether it is species transport, whether it is momentum transport, this parameter changes, and also this one changes, this one essentially changes, and the associated change in this actually becomes the change in the coefficient. So, this viscosity mu ij, that is also now given by 2 times 8 mij times k 0 t to the power divided by pi to the power of half divided by pi sigma ij square. Now, you see importantly this rho is missing here. So, it does not depend on rho. Okay. Now, energy transport, here once again we see that now for energy transport we can write this generalized property xi as essentially n Mij times Et, T whereas E is the internal energy, and then we can write d dz, we will of course when we do d xi dz, we will arrive at d is dz, and we can write d dz is equal to Cv dt dz. Okay. So, d is equal to Cv dt, we can use that one, and then we will arrive at this thing that this well, f energy is equal to minus lambda ij dt dz. Lambda ij is nothing but 8 mij kt divided by pi to the power of half times Cv by this thing. Okay. Now, this lambda is nothing but this thermal diffusion coefficient, or this thermal not thermal diffusion coefficient, it is a thermal conductivity coefficients. Okay. So, this is used in Newton's law of viscosity. The previous one, as you know, is Newton's law of this one is actually Newton's this energy transport is actually this Fourier's law of conduction. The momentum transport is actually Newton's law of viscosity, and the species transport is actually Fick's law of mass diffusion. So, but now one thing that you can see, the most interesting thing is that because these have similar origin, all of them have similar kind of dependence. So, all of them are temperature T to the power of half dependent, and all of them have this kind of similar things. So, that is how we can derive it in a simplified manner, but it is very illuminating in the sense that it gives us why it should depend on temperature. The answer is as we have discussed, that basically because it depends on the mean molecular velocity, alright, which comes from the Maxwell-Boltzmann distribution, and that is essentially T to the power of half. Now, So, what we find is that the density this lambda mu and rho dij, that is if we take this rho to here. So, all these things, and we will see later that instead of dij, this rho dij is sometimes a better choice for defining diffusion. So, we see that this both these things, this lambda mu and rho dij, these things are density and hence pressure independent. Now, why this is density independent? Suppose you give you would increase the density by twice, that you put in twice number of molecules of species I. So, you would think that yes, now my transfer of will increase. Yes, that increases, but you see the distance between which they collide, that L, the mean free path, that also decreases now by half, right. So, as a result of this, now as you know that the mean free path appears proportional here. So, the flux actually depends is directly proportional to the mean free path. Okay. So, so as a result of this, as the mean free path decreases, your this increase of that particular species actually is counteracted, and hence there is no change, there is no this parameters lambda, mu and rho dij do not depend on as such on density and pressure. But the most interesting thing is that they vary with t to the power of half. Actual variation is even stronger, but this t to the power of half gives us a quite a good qualitative idea that it should be increasing with temperature at all the time. Okay. And as you see that the characteristic diffusion rates. Okay. Now, the diffusion rates that might be of choice is sometimes dij. So, dij is proportional to 1 by rho. So, it can be written to be proportional to 1 by t. If we use kinematic viscosity, of course, that is essentially proportional to 1 by rho. So, that also becomes proportional to 1 by p, and thermal diffusivity, which is lambda, thermal conductivity divided by Cp times divided by rho Cp, that also is proportional to 1 by rho and hence proportional to 1 by p. Okay. So, then if you consider these kinds of properties, that is characteristic diffusion rates, mass diffusivity instead of rho, kinematic viscosity instead of dynamic viscosity, and thermal diffusivity in terms of instead of thermal conductivity, because of the density dependent, because they are all proportional to rho to the power of -1, they essentially become pressure dependent. All right. So, now the properties, we are always look for non-dimensional numbers. So, the non-dimensional numbers of choice of importance in combustion, we will also encounter them later, other things, other non-dimensional numbers which are essentially non-dimensional numbers in terms of chemical kinetics. We already have encountered one, which is the Arrhenius number for kinetics, but here we are talking about non-dimensional numbers in terms of transport, and for that we see that the numbers of importance are Schmidt number, which is nothing but SCij is nothing but the ratio of the kinematic viscosity to the binary diffusivity. Okay, nu by dij, and we can also write it in this form, that is dynamic viscosity divided by rho density times dij. We can, of course, Prandtl number is important, but the Prandtl number does not change too much, but still this nu divided by alpha h. This is very important when it comes to combustion, which is essentially Lewis number. Lewis number is the ratio of the thermal diffusivity alpha by molecular diffusivity, that is, or the binary or the species diffusivity, that is dij. Now, this is very important, because in combustion there is always competition between thermal energy transport, heat transport and molecular transport. Okay. So, this quantifies that competition, which one is actually stronger, which one is expectedly will be stronger, because if the Lewis number is greater than 1, it means that the thermal diffusivity wins over the species diffusivity. If Lewis number ij is less than 1, then it means that species diffusivity is winning over thermal diffusivity, so on and so forth. So, that is a very important number. Okay. Now, there are this kinetic theory, if we use, there is also second order diffusion, which is actually observed in reality. What is second order diffusion? Second order diffusion is that when there is a temperature gradient, okay, and you are considering a multi-component species. So, not only heat transfers, of course heat is transferred, but there is also mass transfer. There is mass diffusion when there is a temperature gradient in a multi-component species, and a good example is that there is when the light species like hydrogen goes up the gradient and heavy species like soot goes down the gradient. We will come back to this again later when we discuss about the constitutive relations that come into the define the different diffusive processes inside the governing equations. and before diffusion is the thermal diffusion in concentration gradient, and it's generally not too much important in combustion. All right. So, now as we said that this all these properties, of course, state to the power of half dependence is nice, but this Mij, this diffusivity is not really proportional to Mij. Larger the mass of the molecule, it your diffusivity should not be large, and there are actually two simplified assumptions. As we have seen in kinetics also, we need transition state theory to properly explain different things. Similarly, here also the refined theory is can be used using kinetic theory of gases. Okay. So, here I will not go into the details of this, but what we will just do is that we will just give you a brief overview and what are the parameters, how does the calculated properties look like. So, here the interesting thing is that again we had what is the difference? The difference is that when we were talking about collision theory, so we were actually meaning that this molecule goes and hits these molecules, right. We are actually considering counting the number of collisions, okay, that was happening. So, but here we say that there is but actually these molecules are not billiard balls, right. They have a force field surrounding them, they have an electron cloud, and those electron clouds when has force associated with them. So, we consider that yes, we do not consider molecular structure in these ones, but then the collision dynamics in this case, instead of this hard collision, is described by a central force field which is represented by a force potential. Okay. So, here this instead of this hard collisions, we consider a central force field which is which we consider a force potential which describes actually the force field. Okay. So, we actually consider this molecule to be a point mass. We do not even need to consider the molecular structure, and then the force potential will describe how much collision can happen. And these as you all can understand that if we consider a hard sphere, basically it means that the inside the sphere this potential goes to infinity, but outside the sphere there is no effect as such. So, only after the collision then there is the molecule response. Before that this molecule does not sense that another molecule is coming, but in reality that does not happen. Of course, the molecules have an electron cloud, as I said, and as a result we consider this Lennard-Jones potential which is given by this this kind of a potential curve, and then we do some calculations, and this is the final results that we obtain. So, these are nothing but, don't get worried about this, these are nothing but this collision integrals, and this is some non-dimensional temperatures as you see here, and these collision integrals are essentially one can find tabulated as a function of this T star and D star, which is another length. And what we find here is that for a single component gas, the dynamic viscosity mu I is now given by pi mi k 0 T. Of course, this T you see when you compare this with the collision theory, this T this T dependence remains half to the power of half, but when you go to the binary diffusion coefficient, there is two interesting deviations from the collision theory. We see that now this diffusivity Dij is essentially has a T to the power of 3/2 dependence, and also this Mij has come downstairs. So, larger the m, smaller is the diffusivity, which makes sense now, right. So, but there are other similarities also. So, with this and as I said that we can find this collision integrals tabulated now, and from that we can find a good estimate of these different properties. So, with that we will end this transport will end this transport theory topic, and next we will go on to discuss the governing equations, where we will see that how this transports as well as this kinetics basically comes and along with the convection. So, basically we will see that with the governing equations we can describe essentially any flow field of choice, and that is the purpose of the governing equations, which is a very central theme of any combustion course, and of course it is a very central theme of our course also. So, we will come back to that in a short amount of time. Thank you.